Okay, all right. Thanks to the brave souls that have stayed all the 5 days. Uh, it's not so bad. We've managed to have about 10 people, the last 10 standing. Very good. So what I want to talk about today is actually I'm going to take a slightly different route to what I've been doing in the last 4 days, where I've been a little bit sort of I started with a large overview, but I was trying to get in some sense one's hands dirty by doing a little bit of calculations, and in that manner in between giving flavor of what exactly is the physics of Bose-Einstein condensates. But I realized that apart from a little bit of the first lecture, the aspect of Bose-Einstein condensates that have been emphasized more or less has been more on the many body or the quantum many body side of things, and also some aspects of Gross-Pitaevskii equation and such. So this lecture, I'm going to actually do a slides lecture where hopefully you will see that a large part of Bose-Einstein condensates research involves something that is somewhat more closer to my heart and what I work on, which is quantum optics or atomic physics and so on. So with that in mind, let me share my screen and slowly begin. So I will, again, as usual, stop in between and let me just share my entire desktop. Why not? Okay, I'll stop in between and also make sure that we can have some questions, and let's see how far we get. Okay, so let me get my annotator. Why can't I see my annotations? Wait. Can you all see my pointer? Can someone confirm that you can see my pointer?
Yes, sir.
Okay, fantastic. All right, so here we go. So let me make this smaller. Welcome to the 5th lecture of this series. And so what are we going to talk about today? So one thing I realized is basically I never told you in detail how one goes about making a Bose-Einstein condensate. We've been talking a lot about the theoretical description of how to understand what a Bose-Einstein condensate is and so on, but I've not really talked about how to make it. So I will begin with a brief overview of how, which is 20, 30 years of research, but I will make a very brief overview of how to make a Bose-Einstein condensate, trapping, cooling, and so on. Then I will really talk about Bose-Einstein condensates in optical lattices, which are periodic potentials of light in which atoms are placed. And in this context, I'll describe this very famous experiment, a landmark experiment that actually, in some sense, showed the community the power, the full power of what this Bose-Einstein condensates in optical lattices, or cold atoms in optical lattices, what sort of physics can we address with this very interesting experimental and theoretical tool. So that's going to be the meat of the talk. And then if time permits, I'll come to the study of Bose-Einstein condensates in a cavity, which is in some sense, it's like an optical lattice, but it is alive in the sense that an optical lattice is an applied static potential of light, but a cavity is essentially an applied potential that is dynamic, which changes as the atomic state changes. That's the 0th order description of cavity I'm interested in. And that is very close again to the sort of things I work on and the things that I am interested in. So it might be from a personal point of view, if I can get there, it would be great, but otherwise it's all right too. All right, so let's begin with how to make a Bose-Einstein condensate. Basically, if from what we learned in the first part of the lecture, in order to make a Bose-Einstein condensate, you want to essentially trap atoms, because that's when the density of the atoms becomes significant, so that the transition temperature comes lower. And at the same time, even when the transition temperature is low, you have to trap and then you have to cool them below the transition temperature. So if you wanted to make a Bose-Einstein condensate with neutral atoms, so to speak, you have to learn how to trap them as well as how to cool them. Okay, so the 0th order way to trap atoms is by using magnetic fields. And the fundamental principle that lies behind it is the fact that atoms are not point particles, right? So the For example, if you take the electron in the outermost shell of a sodium atom, an alkali atom, or rubidium atom, this electron has a rich internal level structure with different orbitals and so on. Moreover, very interestingly, once you apply a magnetic field, these energy levels split, right? And these energies can increase, some cases energies can decrease in applied field, and this effect is what is called a Zeeman effect, right? So one can take advantage of this Zeeman effect to make a magnetic trap. The idea is very simple. Basically, the changing internal energy of the atoms, once you make the B field position dependent, this essentially becomes like the potential energy for the center of mass of the atom itself. So the electrons internal energy level is going to depend on position. As a result, the entire atom's potential energy is now becomes B of R. Okay. So now how do you trap? Of course, one can trap at a local maximum or a local minimum of such a static magnetic field. There is actually an interesting result that people proved around the time people were thinking of trapping atoms, that just like there is this Earnshaw's theorem that you learn in electrostatics for electric fields, that it cannot have maxima, there is actually no extrema for electric fields is not possible. Similarly, you can show that maxima is not possible for magnetic fields, but you can actually make a local minima, in which case you should only choose atoms which have a low field seeking. So you want to put your atoms in an internal state such that it seeks lower and lower fields. So this branch, not this branch, right? So you have to then find ways to make configurations of electric currents such that you can realize magnetic field configurations with absolute minima or local minima at some point in space, and then you can collect atoms there. There are different known choices. Here, of course, I forgot to mention this mu, the magnetic moment, is coming from the magnetic moment of the electron, which is Bohr magneton. Of course, the nuclear and the protons, neutrons, all of them have some magnetic moments as well, but those are tiny compared to the electron's moment. Okay. So you can actually trap with such configurations. The most popular configuration, simplest configuration, is called a quadrupole trap. You can actually design it by, you might have seen this in your basic magnetostatics calculations in undergrad, where you put two circular coils with oppositely directed current. You get a minima in the middle. Okay, so such a trap is called a quadrupole trap, and this quadrupole trap has this form. The magnetic field depends on X, Y, Z. So when you basically look at mu dot B, then it gives you basically a very nice dependence where you have a minima at the point X equal to Y equal to Z equal to 0, right? So then there is one small problem with this. The problem is that there is a zero, you're trapping your atoms at a zero magnetic field. This is not very advantageous. This has a problem. The problem is, what are you doing when you're assuming that basically as I apply a position dependent magnetic field, and my atoms move in such a potential landscape created by this, I'm assuming that the internal level of my atom is always on the same branch, right? So it doesn't move to any other internal level states. As position varies, I'm going to move somewhere on this line. But the problem is this motion is not very slow for a hot atom. Sometimes you can also have processes where I jump into one of these higher levels, right? And since the energy gaps between the higher level and the lower level are smaller at smaller B field, very close to zero field, what happens is you can actually, the internal state of the atom can flip from the one that you can trap. Then what happens is you have a quadrupole trap and all the atoms like really go close to the point where you want to trap, and then they just escape. There is a spin flip and they escape. And this is a problem. So it's sometimes called as a hole in the trap, and you can plug that hole by other configurations. This is called a top trap, where you add an oscillating component, and this oscillating component, when you time average it, you end up with a trap of this form, right? So this is a very nice harmonic trap, and it also has a non-zero B field value at the X equal to Y equal to Z equal to 0 problem. So point. So this is like a hole plug. So this is how magnetic traps work. So that's one aspect. So you have a trap, but now you want to cool the atoms. So the fundamental idea of how to cool atoms again involves the fact that atoms have internal levels, but the main candidate for cooling is lasers. So the idea is that the atoms can interact with laser light. So in this case, it's basically the fact that the laser light has an electric field, which is much larger than its magnetic field. So it's an electric field, and the fact that the atoms have dipole moments. This is what causes, this is sort of the fundamental physics you need to have laser cooling. But let's look at how laser cooling works in a couple of scenarios. So the first scenario is basically a situation where I have an atom beam that comes out of some oven, and then I'm going to shine laser repeated. I'm going to shine a very bright laser at it. And from popular science fiction or just some thought, you know that there is some kind of radiation pressure that actually can stop my atoms, right? Or slow down my atoms. So how does that happen? Fundamentally, the quantum thing that is happening there is that the atoms absorb a photon that is coming at them. When you absorb a photon, your momentum, so when you absorb a photon, you get a momentum recoil in the opposite direction to the photon. So if this is coming like this, I lose momenta in the forward direction and I slow down. But of course, if this were the only issue, then I can basically, make all sorts of cool devices with my lasers. But there is another additional feature. Just as I can absorb a photon, eventually an atom can actually spontaneously emit a photon. But our luck and what helps us to actually use lasers to slow down atoms is that this spontaneous emission is essentially, I don't have a picture for that. The spontaneous emission is essentially, which is read by this gamma 0 or this gamma g. This spontaneous emission is essentially, it can happen in any direction. So the spontaneously emitted photon by the atom can go anywhere with some distribution in space, but it can go anywhere. It is not always emitted in the same direction as the original photon. Because if it were preferentially emitted in that direction, then of course you have no momentum loss. But because it can be emitted in this in space in different directions, and it's very randomly emitted, on an average, the recoil that you get due to spontaneous emission doesn't slow you down. It doesn't change your average momentum. As a result, I can basically shine lasers on an atom, on a sort of a beam of atom, and I can cool them down somewhat. So this is regularly used, but how do you do it with atoms? There is a small catch when you try to do it with an atomic beam. And this is got to do with Doppler shift, which can be again exploited to make a better cooling mechanism. But let's first understand what happens when I have like a hot cloud of atoms that is released from an oven and I'm shooting lasers at it and I'm trying to slow it down. So now the problem is, it is true that I can use the process that I said and I can sort of cool down my, my atoms. But as my atomic velocity slows down, because of the Doppler effect, atoms that are moving towards my beam will actually see a frequency that is larger than the applied laser's frequency, right? So if the laser photons in their frame of reference, the laser photons are going to be blue shifted, or basically they're going to be, if you're moving towards the laser beam, you will see a larger frequency photon. And that is a problem because my energy levels that I have for my atoms, they have a particular resonance frequency. If the frequency of the photons is larger, then I'm not able to efficiently absorb these photons, right? So I'm in trouble. So what do you do? So what do you do is very cool, which is you always send in light that is of slightly lower frequency. But now there is the additional problem. As you keep slowing down the atoms, the frequency you have to drive with, you have to make it also different, right? Because the red shift is going to be the Doppler shift, which is to this leading order like this, that is going to be very different depending on VB. If the average VB slows down, the laser light that I should apply omega should also be changed, right? So now, which means as I slow an atomic beam, I have to slowly change the frequency of my laser over time, which is one technique one can use, which is called chirping. Or you can do again this beautiful thing with magnetic fields, where I apply a non-uniform magnetic field along the position direction. And as a result of this magnetic field, it shifts exactly my atomic resonance by the same amount, such that I'm basically changing omega 0. So I can either change omega or omega 0. Omega 0, I can change by applying the magnetic field. Omega, I can change by chirping the laser frequency. Either if I change omega 0 by applying magnetic field, this is actually a very beautiful piece of equipment called a Siemens slower. And so you can use that to cool atoms. So that's what is the first stage of any kind of laser cooling. So once you do that, you get slightly colder atoms than just thermal room temperature or even hotter atoms. But that's not enough. So we have to cool even further down. The second kind of cooling that is employed in these Bose-Einstein condensate systems is called optical molasses or laser cooling in this form, where I have an trapped atomic gas, somehow trapped, let's say, in a magnetic trap. And then I apply from all actually in 3 directions, I apply red detuned laser beams. So there'll be 6 laser beams that are applied on. Let's look at one direction alone and understand how applying these red detuned laser beams allows us to cool. So the cooling mechanism is exactly as before. I basically get photons are absorbed by the atoms, and that absorption is what is causing the cooling. The rate at which my atoms absorb the photons depends, of course, on the dipole moment of the atom squared, the strength of my applied field, but it also depends on this response function, which is basically a Lorentzian function that tells us that the atoms are like an oscillator that can actually just pick up energy precisely at this omega Eg or omega 0, but with some error that is given by their spontaneous lifetime or the width, right? So it will accept anything between omega Eg plus or minus gamma E by 2. But if you apply a frequency far away from omega Eg more than gamma E by 2, the atom simply won't see that light. Okay, so I'm just thinking of a very simple model of an atom with just 2 levels. Okay, and in this picture, what happens here? So what happens is physically something very nice happens, which is if I have an atom that is basically at the middle at exactly at z equal to 0, it will equally absorb left and right moving photons. Okay, and as a result, there will be no preferential force. On the other hand, if I have atoms that are moving at so atoms that are not at all moving, they will see both these frequencies at the same value, and basically they will not preferentially absorb left or right. On the other hand, if I move with positive velocity Vz, right, then what happens is the atoms are going to see the right moving photons with frequency that is actually lower than original frequency. Both these frequencies are tuned to be below the atomic frequency, but this will become even lower, right? So then it will, but on the other hand, the left moving photon will actually be, its frequency will be increased, and it will be, because of the Doppler effect, it's more likely to be absorbed, right? So let's put this into math. So if I look at my right moving absorption of right moving photons, I have to take omega minus my velocity times q, and I evaluate this at omega minus velocity my Vz times q. On the other hand, the left one, which is these photons, they will be absorbed at omega plus Vzq due to the Doppler effect. Now, basically my change in momentum, right? So my change in my average momentum is basically h bar q times the absorption, right? So this is h bar q times the absorption of the left moving photon will give me a h bar q kick, whereas the right moving photon will give me a minus h bar q kick. So that will be my total absorption rate, this part, and that times h bar q is my momentum change. And when you actually write this down and calculate it, you get a very nice answer, which is dpz by dt, the momentum change, has a minus gamma times Vz, which means, and this gamma is a positive number, which depends on this whole thing, not important, but the basic idea is that P is V. So this, you can write it as basically damping of my velocity. So what I get is actually a frictional force due to this configuration of 2 lasers. And this is what is called an optical molasses. And as a result, I am sort of, my momentum slows down further and further. How small can I make my momentum? So if I take a momentum distribution, which is basically P squared average is of the order of kT. So my width of my momentum distribution is kT. I want to be able to distinguish between the right and the left moving photons. That is when I can get this cooling effect, which means if my momentum distribution, once basically the momentum distribution becomes small enough that I cannot do this distinguishing, I basically cannot cool any further down. Basically, once I at temperatures for temperatures lower than this, basically I cannot use the this Doppler cooling optical molasses idea, and this is the lowest temperature I can get to, and this is about order of 100 microkelvins. Okay, so this is what happens at the second, typically the second stage. But there is a more efficient way of doing this laser cooling using a combination of magnetic trapping and laser cooling, which is called the Magneto optical trap. So this is the workhorse of ultra cold atoms and Bose-Einstein condensates, and this works in a very clever way. So the idea now is to have instead of a two-level atom which was absorbing photons with some linear polarization, now I'm interested in an atom with excited states of different magnetic with different angular momentum. For example, my ground state has no angular momentum, but my excited states can either have -1, 0, or +1. So now, if I want to go and absorb, if I want to make a transition to a atomic state with a different angular momentum, of course I have to absorb basically a photon that has some spin, that is, which means I have to be in one of these circular polarized states. Okay, so then the idea is to basically consider a regular magnetic trap like our quadrupole trap, and trap atoms in the center of this trap, and then from the left and the right you apply basically a plus polarized light which couples 0 to +1 state, and a minus polarized state from the right which couples from 0 to -1. Now the interesting thing is the energy level, and you put the laser at some red detuned value. Okay, so the laser frequency is here, these are the atomic levels. Now the idea is basically the gap between the -1 and the 0 and the ground state. Basically, if you take an atom that is at the center and let's say it moves a little bit to the right, so Z becomes positive, right? So let's call this Z, and Z becomes positive. Now, what happens is basically the M equal to -1 state, its energy decreases because of the Zeeman effect, because of the magnetic field configuration, right? Now, as a result, my laser frequency becomes closer to my atomic frequency, and hence I absorb more of the light, sigma minus light, that couples 0, the ground state, to the -1 state, which means I'll absorb more of the laser light that is coming at me, which means I'm going to get kicks towards the Z equal to 0. And you can see from this configuration that the exact opposite happens when I move to the left, right? I absorb more of the sigma plus. So with this clever scheme, you can really cool atoms down a lot. Okay, so you can get them down to typically, if you make a very good MOT, to even lower than this 240 mu K. But once you have done that, that is still not enough to make a Bose-Einstein condensate. The final step in cooling is actually in a sort of a cruel twist of fate. In some sense, people found out all these clever schemes to make cool down atoms, and there are Nobel prizes for this kind of laser cooling that were awarded. But the final step that one had to do to really get to the Bose-Einstein condensate was literally something that happens every day. So I'm drinking a cup of coffee, and I took the coffee when the lecture began, and it's super cold now. So what has happened? Basically, there is like a hot vapor. So some part of the water in the coffee was vapor state, and those hot vapors have evaporated. So you basically make a way to take a gas of atoms that is at some temperature, and you cleverly find a way to kick out the most energetic atoms. Okay, when you do that, immediately you get a state that is non-equilibrium. It's not a thermal state anymore, but then the atoms have interactions, they collide, and they settle down to a thermal state. But now the thermal state will be of much lower temperature. Okay, the way you do that in an ultra cold atoms experiment is, after you've made the temperature to a certain value with the MOT, you transfer to a purely magnetic trap like this quadrupole trap, and then you apply basically RF pulses which flip the atoms from a low field seeker, which is trapped, to a high field seeker that will leave the trap. Moreover, you choose the RF frequency such that you basically only flip atoms that are far away from the center at higher energies. Okay, so you can choose that frequency. So the atoms that are already at lower energy don't get kicked out, but the atoms at higher energy get kicked out, and that lowers the temperature a lot. Okay, this is the final step of Bose-Einstein condensation. And after that, you actually get a Bose-Einstein condensate. So to summarize, what is the typical full sequence of Bose-Einstein condensate to produce a Bose-Einstein condensate that is followed? For example, in this landmark paper that we have seen a few times now, atoms come out really hot from an oven. You use this Siemens blower and a laser that is applied from here, and it cools down the atom further. And then this allows a slightly hot but still not so hot cloud to be loaded into a motte. And because of this motte, you trap a bunch of atoms in this motte. Then you turn off this motte and purely have one of these magnetic traps. So in this experiment, they did this top trap with this oscillating field with the hole in the zero plugged. And once you have that, you basically apply RF flips and implement this evaporative cooling. Once you implement this evaporative cooling, voila, you have your Bose-Einstein condensate. Okay, so this is the magic that is done to actually get these objects we've been talking about for the last 4 days. And all of the considerations we made would be just meaningless theoretical things if not for these beautiful experiments. So I thought I should definitely give some attention to them. So I will stop at, and also because they have very beautiful quantum optics. So I will stop at this point before I move on. If there are any questions, I'm happy to take them now.
No, sir.
Yeah.
The last method that you mentioned that finally does the job. Do we have to do all the other things like laser cooling and the Doppler cooling and all those things to get to the point where we can use this method, or can we do it from the beginning?
No. So you really have to do all of the other things to do this method for a very, very cute reason. The cute reason is as follows. You see, the success of this scheme is not just allowing the fast moving atoms to leave. Whatever is left should be able to thermalize, which means you should have enough of this density, or more accurately, what is called this phase space density. So this n lambda cube should be significant enough so that there are enough collisions for the gas to thermalize to a lower temperature. Otherwise, you get some non-equilibrium state that is never going to be a Bose-Einstein condensate. That's why you use the first cooling process to get enough cold atoms with enough density so that finally you can do this evaporative cooling. And in fact, even though I framed evaporative cooling as some, junk, simple idea, the whole point was how do you get, everyone knew you have to do evaporative cooling at some point, but how do you get to that stage and how do you combine it with this laser cooling? That is where the whole genius of Eric Cornell, Carl Wyman, and Ketterle and all the other people, that have worked on it. So that's really required a lot of technical stuff that I can't cover it here. B, I don't know a lot about it myself as a theorist. But that it wasn't easy, let's say. It didn't take 20 or 10, 15 years for these people after laser cooling, 1990 laser cooling. Laser cooling was known in 80s, and I took like over 10 years to get to a BEC. So it is non-trivial how to get to it. Yeah. Did I answer your question?
Yes, sir, partly, but I think I'll have to read up more to really.
So basically, you have to do enough cooling so that the density, you have to cool and collect enough atoms, without which you can't do evaporative cooling. That is the main idea.
Yeah, I understand that.
Okay. Also, if you are putting something in the chat, somehow I can't see the chat so well. Okay, now I can see. Okay, in this case, the environment is always hotter than the sample. How are we shielding the sample from environmental effects? Very good question. One thing I never mentioned in this is everything is done at very high vacuum. If you don't have a vacuum chamber, you cannot do any low temperature or high or Bose-Einstein or quantum optics experiments. The good quantum optics experiments need high vacuum as well. So that's how you remove all the environment atoms that are hotter. Okay. Are there any further questions? You can unmute and ask as well if you want. Okay. If not, let me move on. Okay. Good. All right. So let me move on to the second part of the lecture, where I want to understand the theoretical and aspects of what happens, what is these optical lattices, how do Bose-Einstein condensates in optical lattices work. Okay, so basically the idea in an optical lattice, as I mentioned, is to apply an electric field produced by a standing wave of light. Okay, how does the electric field and the atom interact? It is basically a dipole coupling with D dot E. So the dipole moment, of course, is a quantum operator for an atom. In the simplest case, of course, a dipole moment is this Q times R, and you can expand it in the internal levels of the atom, and it will basically have transitions between different levels. But if I'm going to attack with some periodic variation of light, so some actual laser light with a fixed frequency, I can basically just worry about two atoms that are nearby resonance to this applied field, and I can expand my dipole operator in this very simple two-level form. It's like a pseudo spin half operator if you want, quantum mechanically. With that, what can I do? My original states basically is, my original Hamiltonian is EE minus GG with the resonance frequency EE minus EG. And now I can treat this sigma plus sigma dagger, which is basically EG plus GE. So it causes transitions between E and G as a perturbation, and do second order perturbation theory and write down how my ground state of my atom is shifted due to the application of this electric field. And I can write it in this manner, where this is a time average over the electric field, applied electric field square. The intensity is time average times and quantity alpha of omega, which depends on the atomic properties and which is called the polarizability, single atom polarizability of an atom. Of course, it depends on the strength of my dipole moment, but it also depends on how close I am to resonance. EE minus EG minus H bar omega is the laser applied frequency. Okay. Now, of course, in general, my atoms do not have perfectly well-defined resonance lines. There is always some width, which is basically the spontaneous emission rate. And so this alpha of omega is a complex object. So I can absorb photons. We studied that in a moment ago. As a result, my shift is actually has two components. One is a conservative, it's called a conservative form. I'll call this conservative potential in a moment for a reason I'll come to, but it also can have a imaginary component. For these optical lattices and the kind of things I'm going to describe, I'm typically going to ignore this spontaneous emission in this case. Okay, so now what is happening? So all that I have is I can write my basically I can write my result of applying an electric field on my atom as basically providing an external potential Vg of this form. Okay, now this does a time average, but I can have some spatial dependence of the electric field, right? So that spatial dependence, all of it goes into this so-called Rabi frequency. And basically, if I set gamma to 0, my potential just becomes h bar omega squared by delta, and omega squared has a magnitude of the applied electric field and also the position dependence of the applied electric field. Okay. So the entire idea is, as soon as I apply an electric field, that is, if I have an electric field applied, it produces for me in this limit, once my detuning delta, which I have defined here as the difference in frequency between the resonance frequency of the atom and my applied laser frequency. So if I apply lasers of slightly different frequency, in fact, significantly different frequency from the transition, so that absorption is not so important, the light fields, applied light fields, effectively give me a conservative potential whose shape is set by the position dependence of the applied electric field. That is the idea that one exploits to make a so-called optical lattice, which is simply applying a standing wave of light And atoms, essentially, because of the fact that this is a standing wave, let's just consider a standing wave in one dimension, and it takes this form. Once you do the time average, this standing wave basically gives you a position dependent potential, or a potential that has exactly this form. So it gives you a position dependent periodic potential with the periodicity precisely set, in this case, by the half of the wavelength of the applied light. Okay, so that's 1D. But of course, what stops me from going to multiple dimension? I can basically apply lasers in all three directions, and I can make three-dimensional lattices, two-dimensional lattices, lattices with all sorts of crazy geometries if I want to simulate condensed matter systems and so on. Okay, so this is an example of a three-dimensional lattice. For example, if I apply three lasers, I can, six lasers, and make three standing waves, or a larger standing wave in 3 dimensions, I can get a potential of this form. Okay, so now the idea is, at the end of the day, once I have understood the quantum optics of how to produce an optical lattice for my atoms in the ground states, which is the state in which I make my Bose-Einstein condensate in this ground state, meaning ground state of the 2-level system. So in this ground state, I make all the atoms are in a Bose-Einstein condensate, and this Bose-Einstein condensate and these atoms basically see a periodic potential in space. So this optical lattice is just a light-induced periodic potential for quantum mechanical atoms. Okay, that is the main thing to take care of. Now let's think a little bit about the different energy scales that occur in the atomic case. So one energy scale is basically the one can think of it in 2 ways. One way is basically if I have a laser that has photons of momentum q, which is related to the periodicity of my lattice. This basically is the recoil energy. It is the, if I absorb a photon of h bar q, my atom will feel an energy change of h bar q whole squared by 2m. So this is called the recoil energy. Also, in another way, this is also telling you how localized, in some sense, is your lattice spacing. So as in how tight is your lattice. So this D, it also gives you a sense of the lattice constant. Okay. So now what one can do is to understand what is a big or a small lattice. The idea is that the ratio of the applied potential in units of this recoil energy really tells you if the potential you've applied is how big a potential barrier it is. If you want to say that, if you think of quantum particles tunneling in this landscape, how well they can tunnel, that is in a sense set by the barriers, and you can actually understand that by seeing the ratio between the applied potential strength to this recoil. The way to see that is, I can, roughly speaking, I can think of at the bottom of my wells, I can think of as though I have an oscillator potential with the second derivative of the applied potential, which is actually nonlinear and it has this cosine form, but at the bottom it's like an oscillator, and it gives me some oscillator frequency. Now, if I take the ratio of this oscillator, the oscillator length implied by this oscillator frequency, which tells me the extent of the wave function when I put an atom at the bottom of this well, to basically the separation to the next well D, that is precisely given by E0 to V0. So now if V0 is much, much greater than E0, the extent of these individual wave functions are going to be really tiny, right? And I cannot get enough tunneling to the next well. But on the other hand, if V0 is much less than E0, opposite happens, and my wave functions are delocalized and the atoms can basically move freely in the lattice. So a large lattice strength means the applied potential V0 is much larger than the recoil energy of the atoms, and these and so on, and vice versa. Okay, so that's just to give a sense of the energy scales in an optical lattice. Okay, so now I'm slowly moving towards this description of this Mott insulator superfluid transition, for which we have to understand a little bit the quantum single particle states of quantum particles in periodic potentials. We've already understood it for free space, which is plane waves. Let's just quickly revise. I think some of you might have already seen this in condensed matter courses. So the eigenstates, for example, in a periodic potential, this is in 3D, are given by these block states. this have this very nice property that they are a plane wave times a periodic function. It is periodic in the lattice parameters. So if it's cubic lattice, it is repeated over a the size of the size of my lattice constant, or D here as I'm using. And of course, these are energy eigenstates of my system. And so the lowest energy eigenstate has this K is called a quasi momentum, because this is not perfectly plane wave. It's not a momentum in that sense. So the lowest energy state has K equal to 0, and there is another index nu, which tells me what is the band. And one can just specify this quasi momentum is a special kind of wave vector, which is unique only in -1 to 1, in the sense that if it goes from minus pi over the periodicity to pi over the periodicity for a 1D system, which is the reciprocal lattice, which is the size of your first Brillouin zone. So beyond that, it is basically repeating. And these repeating things you can fold back and make a picture that's called a band structure, right? So this is just the one-dimensional band structure. This is how the energy eigenvalues of a single quantum particle in one of these optical lattices is going to be, okay? Now, this is one kind of basis functions into which our many particle system can occupy, but a more another different basis that is very useful in discussing the physics of Mott insulator superfluid transition is the situation where I take basically a Fourier transform or a sum over many block functions. When I do that, because these block wave functions are delocalized in space, their Fourier transform gives me localized wave functions. And basically these wave functions are called the Vanier functions. And these Vanier functions are, depending on the strength of your lattice, they can be very strongly localized at the minima of my potentials, which I'm going to call as sites of my lattice, right? So these are the minima of my lattice, minima of my optical lattice potential. Now, if I write down the many body Hamiltonian for just multiple quantum non-interacting quantum particles in a periodic potential, V of R given by some periodic potential, I can essentially write it down in terms of creation annihilation operators to create or annihilate atoms into block states, or I can basically occupy lattice side by side. Okay, so either way I can write down this Hamiltonian in either basis, right? So if I write it in the block basis, of course, this is completely diagonal. Ek nu is basically the energy levels that I have here. And A dagger K nu, A K nu is just counting the number of atoms in such states. Okay, that would be Hamiltonian. But on the other hand, I can also write this this Hamiltonian in the Vanier function basis. And when I do it, if I write it in the Vanier function basis, I get this very well-known version of the Hamiltonian of particles in a periodic potential called the tight binding Hamiltonian. After a little bit of simplification, this tight binding Hamiltonian really gives you the following sort of picture. It is just each individual well has some energy, and you have a sum over I with AI dagger AI plus 1. AI dagger creates an atom at the position I, the minima ith well of your lattice, I plus 1 and I different I's are like that. So now this term precisely talks about tunneling of the atoms between different sides of your optical lattice, and J is the tunneling strength. Typically, once I make my V1, 2 recoils, I can safely cut off. In principle, I can tunnel, because I have delocalized wave function, I can tunnel to different, from site 1 to site 10 or site 20 far away. But one can, once my potential strength is large enough, only nearest neighbor tunneling is enough. And that is why I have written it as AI dagger AI plus 1. Okay. And I can also restrict the physics to a single band, because the higher bands are at a different energy, and I'm always going to be in a single band picture. Okay. So this is the physical description of basically atoms in an optical lattice. Now, if these atoms are bosonic atoms and they have this contact interactions, okay, of course, now I have to plug in this psi that I was writing here in terms of, originally I was writing psi in terms of just these, let's write psi, expand psi in the Vanier creation operator basis. And when I did that, I got the tight binding model when there were no interactions in my Hamiltonian, right? Now, if I have interactions like this, I also get this extra term that describes my interactions between the atoms. Okay. So now this is the Hamiltonian that describes an interacting bosonic system on an optical lattice. Okay. And this is called the Bose-Hubbard model. All right. Okay. So now, before I go on and talk about this Bose-Einstein condensation superfluid Mott insulator transition, if there are questions, you can ask me now. Okay, if you're asking questions in the chat, I have a problem. Okay, good. So since there are no questions, let's move on and study this properties of this bosons in an optical lattice. Okay, so the main question one asks, the central question of this superfluid Mott insulator transition okay, so why am I writing this as BEC superfluid Mott insulator transition? I'm just trying to not be disingenuous because I haven't really talked about superfluidity in detail in this series of lectures. For our purposes, I'm going to interchangeably use the concept of a BEC with a superfluid. Any BEC that you make with interactions between them, between atoms, will give you a superfluid, basically. Okay. So with that caveat, that's why I'm going to call this superfluid. But whenever I'm saying superfluid, imagine that I'm talking about a Bose-Einstein condensate. Okay. So we are interested, what is the main question in this superfluid Mott insulator transition business? The idea is to take a Bose-Einstein condensate in an optical lattice and then ask the question, what happens to the many body ground state of these atoms as I make the interaction between the atoms stronger and stronger and stronger compared to the tunneling strength, right? In principle, the way one does that is you can make the tunneling strength larger and larger and larger, smaller and smaller and smaller by making the lattice deeper and deeper, right? So effectively, you can boost the interaction strength with respect to the tunneling by making that happen. And then one can ask, what really happens to my many body ground state? Of course, something interesting happens. That's why we are asking this question. And we will now explore the theory behind what happens, as well as this famous, as well as briefly examine this famous experiment from the group of Emanuel Bloch in 2002, Emanuel Bloch and Ted Hensch in 2002. And the theory, of course, was from Ejagst and Zoller in 98. So the theory was proposed in 98 and the experiment was done in 2002, which is again one of the most heartening features of this entire field of ultra-cold atoms or Bose-Einstein condensate. So basically this was during, this was proposed during the PhD of Ejagst, I think, and then it was implemented essentially almost by the time he finished his PhD or when he was in his postdoc, which is very rare in theoretical physics, that you propose an idea and then it gets implemented. But in these ultra cold atoms, there is a hope for that. And that is really one of the most driving forces for why this is really exciting. Okay. For a theorist, that is one aspect that is very interesting, right? So that your theory can be realized in an experiment. Okay, so let's examine what happens. So now, if I'm in this, let me qualitatively understand why I expect the state of my system to be very different for small versus large interactions, or for small u over j versus large u over j. So let me look at this first, this extreme limit where essentially u is 0. So my tunneling is very large. So I just have a lattice, very nice, with some weak lattice strength. So my u is practically 0 compared to the tunneling strength, right? So the tunneling strength is larger if my lattice depth is smaller. Okay, keep that in mind. In this limit, it's very simple. We just talked about, this is exactly the non-interacting limit of bosons in an optical lattice. And if I make a Bose-Einstein condensate, of course, all of my atoms in my Bose-Einstein condensate will occupy the same single particle state. In this case, the single particle state, which is the ground state, is a Bloch state of quasi-momentum 0, which is represented by phi of r. And this is given by a superposition, right, of different Wannier functions, which are the localized functions at the lattice sites of the atom of the lattice, which are localized at the minima of the lattice. And there is a, basically, if you write the creation operator, creation operator corresponding to this block state. It is a superposition over different localized operators, right? And then what we are saying is in this regime, our atoms are going to be in a Bose-Einstein condensed state with all atoms occupying a delocalized atomic wave on my optical lattice. So this means that basically atoms can hop freely between everything is described by a BEC wave function, but the BEC wave function is now a block wave, and hence there are no fixed particles on each site. If I look at the fluctuations of individual particle numbers, so AJ dagger, AJ squared, that will not be, that will basically, there'll be large fluctuations of that. And the second aspect, because I have essentially a Bose-Einstein condensate, the reason why one calls this superfluid in a very nutshell way is to go back to what we studied yesterday, which is the excitation spectrum. This was for a uniform gas, but for a very weak lattice, it is almost like a uniform gas. And what we see is that when you look at the excitation of such an uniform Bose-Einstein condensate, the excitation spectrum, there are excitations available at very small energies and essentially very long wavelengths, which means I can excite my system, and actually the system will accommodate an excitation at essentially zero energy. At the end of the day, you can think of superfluidity as basically something like this, where my Bose-Einstein condensate, if I allow it to flow, it will flow without any resistance because I don't need to provide any energy for it to move. Even at very long wavelengths, I have motion. So, and the other idea is that excitations are all of very long wavelength, meaning I have essentially coherence between different sites. That coherence between different sites, one can also understand it as basically from this operator, which is creating basically a superposition over many localized states, right? So these are all the features that tell us at very, very small interaction strength and large tunneling, I have a Bose-Einstein condensate or a superfluid. Okay, so if I kick this atoms in this state, they will flow without resistance. Okay, I haven't explained this in detail, but that's how it is. Now, what happens in this opposite limit? So let me go to this extreme limit where I have made my lattice so strong that there is no hopping between different sides of my lattice. Then I know for sure that I have, in some sense, I cannot have atoms delocalized between different sites. So I have to really tell how many atoms are there in each site. Okay, so the state for such a situation could roughly be like this. So in the jth site, in each site, if I have an atom number of sigma, basically my total state is basically of this form. Right, so it is AJ dagger to the sigma. In each site, I create sigma atoms in the localized state. Okay, now this state, I want to show that this is kind of an insulating state or an insulator. How do I show that qualitatively? The idea is, let's ask when I have sigma atoms, when I have this kind of situation where I have basically filled in each site sigma number of atoms. Now, in such a situation, if I have to make an excitation in my system, which means I want to move basically one particle from a site with sigma plus 1 atoms to a site with sigma minus 1 atoms, right? So that I can make each of them have the same number sigma of atoms. This is like an excitation in my system. Now you can calculate the energy of this excitation. There is no tunneling. It's only the interaction energy. You can calculate it. This is the situation before, right? When I had sigma plus 1 atoms in one site, sigma minus 1 atoms in another site. Then I basically did the swap, and basically I have sigma in each site, and then I take the difference. It is precisely U. So in this scenario, each excitation that I have to create on my many body state requires a fixed and in fact large energy U, which is given by the interactions. This is repulsive, and so there is no, I have to pay energy cost to put an atom into a site that has atoms already. Okay, so which means there is always a gap that is a gap in energy that is there, And if I basically make infinitesimal push to my system, it will not flow, right? So I have to give it energy that is over this U in order to get it to flow, right? And that is precisely what an insulator is. Okay. So now one can actually calculate what is the chemical potential in this system. I will just show this in a moment more in a more quantitative manner. And it turns out that it is basically proportional to U times the integer part of the average number of particles per site. Okay. So it is basically you calculate the total number of particles divided by the number of sites. That is the average number of particles per site. Okay. So that is the qualitative picture that tells us that extremely large U, I would expect a state like this. And at extremely small U and large tunneling, I would expect this superfluid. And these two quantum states are very different quantum mechanically. This is an insulator, whereas that is a Bose-Einstein condensate with coherence. And basically, as you change this J over U continuously, you will get a phase transition between these two very different many body states, which is this superfluid Mott insulator transition. Okay, so all right. Okay, so let's look at this a little bit in a little bit more detail. Again, I'm going to be somewhat wishy-washy here. I'm going to hand wave a bit, but that's the best one can do given the time. Okay, so now one thing we will do is instead of analyzing the Hamiltonian and looking for the ground state, which is the point. So we want to look at the ground state of the system as I tune this J over U. Instead of doing that with the Hamiltonian, what is better here is to actually look at this grand canonical potential H minus mu n. Why is this useful? This basically says that we only have the average n fixed, and this is somewhat easier. I won't go into the technical details, but typically this is somewhat easier to analyze than the Hamiltonian, in which case you have to by hand always implement the constraint that I have the same number n of atoms, which is somewhat harder when you are calculating things. So just as the thing that I remarked earlier. With that, we have our, and then you can make a little bit of changes. Like for example, when you write H minus mu n, you get something like this, and you can transform your interactions also into this simple form, Ni times Ni minus 1. This is like density interaction at each site. Ni is the number operator at site I. And then if you assume that basically all of my sites have the same ground state energy, which is fair enough in a perfectly symmetric lattice. If I don't apply any external trapping potential over and on top of this optical lattice, this EI is same, and it's just, you can remove it. It's a constant addition. And of course, this is not exactly the case in experiments, but this is good enough for our understanding, our analysis. So this is our Hamiltonian, or I'm just going to call this the Hamiltonian. This is called the grand canonical potential or grand canonical Hamiltonian. And now we can analyze what happens to the ground state of this system as we tune U over J. Okay, let us look at this extreme case when I make J equal to 0. Then this K becomes a sum of individual independent terms on each lattice site, and it is given precisely by this U over 2 Ni minus 1 minus mu Ni. Okay, and now it becomes immediately clear that the eigenstates of this are basically Fock states with a fixed number n on each site. Okay, then the value that your ground state takes is essentially fixed by the integer value of mu over U plus half. This n is precisely the number of particles in each site is fixed by the value of the chemical potential to U. Okay, so that is my state in the J equal to 0 limit. This is just making the Fock state that I wrote down. I'm making a more concrete argument for it. Okay, so now what we want to do is, now we have this qualitative suspicion that as I add this tunneling and the tunneling becomes larger and larger compared to U, I am going to lose this Fock state. I'm going to go from this Fock state as my ground state to an superfluid state. And now all that, the only theory I'm going to discuss today is how do you calculate the critical value at which I can go from this Fock state or this Mott insulator state with each site occupied with some Fock state to a superfluid. What is the critical value? How do you calculate? One method to calculate it. That's all we are going to do. So the way to do that is simple. It has two steps. The first step is the fact that I have to introduce this tunneling term, which has AI dagger AJ, AJ dagger AI. And I take this tunneling term and I want to introduce it as a mean field, as a perturbation. And I'm going to perturb my energy eigenstates, which are Fock states, and calculate the new energy eigenstates under this perturbation from the tunneling. The second thing I want to do is I want to make a mean field ansatz for my perturbation, where I assume that this AJ dagger, these have a finite amplitude. This finite amplitude is a feature of having a superfluid state. You can see that immediately by going to what sort of state we have in the superfluid. In the superfluid, we have basically occupation of this k equal to 0 state. And if you look at the condensate wave function, that has amplitudes to be in different positions, different lattice sites. The amplitude on different lattice site is precisely this mean field parameter psi that we are taking. Okay. And we are taking in the simplest sort of approximation that it is the same mean field across different sites. Okay. And now the idea is, once you do that, this tunneling term becomes very simple. It becomes like an individual perturbation to each of the site. Each site has this Hamiltonian in terms of AI dagger AI, and it has basically a perturbation given by this JZ psi AI plus AI dagger. And now we will find the value of this order parameter self-consistently. And of course, a Mott insulator is a scenario where this self-consistent value for psi should be 0, right? Because in that case, I can completely ignore my tunneling. That is the fundamental idea. Okay, so now let's just write down the expression for this perturbation theory. Very simple first order perturbation theory for the state. And once I write down the perturbed state, I can calculate the value of this AI, which is my tunneling parameter, which is same for all j, and I can calculate it. When I calculate that very nicely, it brings me to this right-hand side. So I get a self-consistent equation that gives me psi equal to z psi times this response function chi, which depends just on the chemical potential and the interaction strength U. And now I have my answer. So now the idea is that if I write this equation down, it has two solutions. Either psi equals 0, and this solution psi equal to 0 is valid as long as this characteristic equation of this chi equal to U or Jz has no solution. Okay. As soon as this has a solution, there is a chance for psi not to be 0, which means I am going to go from a Mott insulator to a superfluid. So I can basically take different values of mu and different values of j and different values of average n, different values of n of the number of particles per site, and calculate at what point do I basically get a solution to this equation. So for example, here I start here and I keep calculating, there is no solution, boom, I find a solution. Then I have crossed from this Mott insulator to a superfluid. And when I do that, I basically get this phase diagram with these lobes representing Mott insulator states, and outside the lobes having a superfluid. And from this, you can predict at each value, when do you get when do you get a transition from a Mott insulator to a superfluid. For this 0 case, the critical point is given by U over J. By the mean field theory, you get an answer which is not so close to this, but you can do a numerical simulation, and you can find the exact value, but the mean field comes close, but it's not super close. But this is just the basic sort of theoretical description of how you would go about talking about this BEC superfluid transition. But of course, there are more and more sophisticated methods, including better numerical methods, even theoretical methods are there, which unfortunately, due to the lack of time, I cannot talk about. But that's just to give a rough idea of what happens in this transition. Now, let me finish this part by looking at the experimental observation of this superfluid Mott insulator transition, which is one of the landmark achievements in ultra cold atoms. So again, I'm going to be it's just a very overview of it. So the idea is, as with all of these ultra cold atomic experiments, how do you do this experiment? You load your atoms into this optical trap. What does that mean? You take your magnetic trap and then you switch on this periodic potential. As you switch it on to certain lattice depth. So when you switch it on to a certain lattice depth, and you allow the atoms to go to their ground state. And then once their atoms have gone to the ground state in this many body setup, in this applied optical lattice potential, you turn off the optical lattice and you let the atoms expand and you look at the density distribution. Now, for very small lattice depths, if you're ramped up to, let's say, small lattice depths, in which case you expect a BEC or a superfluid, what happens is that when you look at the density distribution after time of flight, it has very clear peaks at k values given by pi over d. Or in other words, in this case, the different atoms in the different wells are acting as though they are coherent sources of waves, and their interference between them comes out very nicely in the density distribution. The other way of looking at this is to also imagine that if I am in the block wave, I have essentially a block wave which has peaks at different k. So if I expand my block wave solution that I wrote down here, very briefly, let me go here. No, after the optical lattice. Yeah. So if I take this UK nu and if I actually expand it in a Fourier series, I will have amplitudes at different k values. And my density distribution in my lattice is precisely going to have peaks at those k values. Right? So if I had a block wave function, if my Bose-Einstein condensate is in a block wave function, I better expect this interference pattern. And this interference pattern also arises from this idea that this individual AI's averages are actually finite, and they are given by this psi that we wrote down. So this A has to be finite in order for this interference pattern to happen. So this is basically the Fourier transform of the BEC wave function in all of the atoms in the ground state of ground in the k equal to 0 block state, for instance. And of course, this is basically AI dagger AJ's average. So you need correlations between different coherence or correlation between different sites to exist. If that is not there, you do not get this interference pattern. So what happens is, as you keep increasing the lattice depth to which you ramped, you see after a point, this interference pattern completely goes away. When your lattice depth is very large, you have reached this limit where your U over J is very large. Your J has become extremely small and the interactions have 1 as the highest time scale. And at this point, you have an insulating state. And this is the evidence of the insulating state is in this time of flight absorption image. For the superfluid, you get a very nice peak structure like here. And for the Mott insulator, you get this completely diffused state where there is no peaks. That was in 2002. Things have become even more cooler now. This is a recent experiment around 2010s where you can actually make one of these Mott insulators and not study the momentum distribution, but use what's called a quantum gas microscope, which is a very high resolution imaging system of an optical lattice, and literally look at the fact that you really have a single atom at each site. Each dot here is basically one lattice site of my optical lattice. At lower lattice sites, when I take a picture of my optical lattice, I get some distribution. And if I keep taking pictures at one time after another time, I will see the atoms moving around a lot. On the other hand, once I get to this extremely large lattice depth, I get this Mott insulator where at different times, if I keep taking pictures, there is perfect unit filling, and I can really count these atoms in, and I can really image the atoms in a Mott insulator. So this is literally one of the coolest pictures that you can find of a many body system, where I can take a many body system and take a snapshot of its individual components, which can completely change the sort of questions you can ask of this many body states. You don't have to ask average questions anymore. You can ask very beautiful questions. And this is again, it is by the same person, Marcus Greiner. He was a student here, and this is from his group now in I forget, MIT or somewhere else. So that's where we are with this mod insulator superfluid transition. So now the time is, I have about 20 minutes. I'll stop here and take some questions. It would be nice if you can also unmute and ask the question. Let me see while I'm looking at the chat. Does anyone want to unmute? Okay, so if not, let me just read the questions. So one question, in Mott insulators, I've come across something like spin liquids where the spin of the electron flows, leaving behind its charge. How does it make sense? Okay, so this is somewhat of a more exotic phenomena. This is called spin charge separation. I'm not an expert on this. Let me just say what I know of it. In some electronic systems, strongly correlated electronic systems, in order to describe certain counterintuitive bulk properties. For example, I'll have like a situation where my magnetic probe will tell me I have, let's say, a particular kind of ordering, in which case I do not expect thermal transport to be significant due to the spins. But on the other hand, when I do a transport measurement, I will see transport. Then one is somewhat flummoxed and asks, exactly how can this happen, that I have a many body state of my degrees of freedom where it looks like the degrees of freedom are frozen, but certain aspect of the degrees of freedom seems to be still doing some conduction. Okay, so then if the frozen aspect of the degree of freedom is its a spin, whereas the transport is done by its charge, then one can imagine that the actual degrees of freedom, the emergent degrees of freedom of my many body interacting system is not the original system with electrons with attached spins, but these are some strange quasi particles where I can actually uncouple the spin and the charge, and they can flow independent of each other. So this is rather exotic, and this is sort of a popular science level explanation, and I have also not done computations of such things, so I can't say much more than this popular science picture. This can happen in certain strongly correlated systems, but to my knowledge, in an ultra cold atomic system, this has not been shown yet. Spin charge separation effectively has not been shown. In fact, magnetism with ultra cold systems is a slightly hard topic in itself. Okay. Aditya is asking, can you once again give the explanation of the superfluid definition that you described as a BEC that flows? Would that still be considered a Bose-Einstein condensate? Okay. Let me say what I'm saying. So what I'm saying is that, let me correct maybe the way I said caused confusion more than clearing up confusion. What I was saying is that superfluidity can be understood as one property of a interacting Bose-Einstein condensate. And the idea is that basically, if you somehow manage to put a Bose-Einstein condensate in one of these capillaries, now the capillary will also, of course, have to be made by some light-induced potential, then you will get frictionless flow at the velocity that is precisely given by the gradient of the phase of the BEC wave function. This is one way of understanding superfluidity and the connection to Bose-Einstein condensation. The second way of understanding it is from the excitation spectrum. The basic point I was trying to make is the following. let me go to the excitation spectrum. Where was it? Ha. So this is the excitation spectrum of a Bose-Einstein condensate we found by solving this Bogly-Lebov equations, right? So now the idea is, if you think of like how superfluidity, let's say from the helium days, how do people understand it conceptually? Conceptually, what is happening is somehow my atoms of my helium fluid at very low temperatures, when I put it in a real capillary, they are able to flow without friction because somehow they go into a very interesting quantum state involving many of the atoms, a collective state that somehow can screen the impurities that are present on the capillary wall. The capillary wall will cause some friction, but I'm able to screen this friction because it is not individual atoms that are actually moving. If individual atoms are moving, they would scatter off the wall and basically give me friction. That is the microscopic picture of friction that would come. But that is not happening. But somehow these atoms are collectively becoming into some very strange quantum state, which we know at least as partly coming from having a Bose-Einstein condensate now, which allows me to flow without resistance. Okay. So this picture of superfluidity tells us that if you want a superfluid, when you excite your system should be able to respond collectively. Okay. And if you remember yesterday, when we looked at this phonon excitation, it precisely was an excitation of that nature, because in this long wavelength, I'm actually involving a large part of my cloud, which means many of my atoms are participating, or in other words, these are collective modes, right? And of course, once I look at very small wavelength or very large wave number, of course, I pick up my spectrum actually becomes EQ0 plus NU naught, which is a gapped spectrum, right? So I need an minimum energy that is like single particle excitations. So the possibility that I can have such long wavelength excitations as the low energy behavior with this dispersion that is going as K, that feature of my Bose-Einstein condensate is again in line with the idea that the flow properties of my Bose-Einstein condensate will be superfluid. I don't know if I answered your question, but I hope, let's see. Do you want to say something? Whoever asked the question. Okay. All right. So what is the time? We are almost, okay, let me, I can't see the time on my screen. Look at my watch. Oh, there is only 10 minutes. So then let me not go into this cavity QED and Bose-Einstein condensate part, because I think that is a game in itself, and that's a very interesting thing, but there is no point sort of half baking it and talking about it. But the overall thing I wanted to say is essentially the idea that once you put atoms in cavities, this one slide I will just show and tell you what is happening, and that's all I want to say. So once you put atoms in cavities, what happens is basically the following. So you get, this is like a Bose-Einstein condensate in a cavity. I've completely ignored the S-wave interactions. So all that I have is a Bose-Einstein condensate, and the cavity has a standing wave of light inside, and basically this gives me this is like the equivalent of my Gross-Pitaevskii equation. So this is like an optical lattice, except now the intensity of my optical lattice is basically given by the electric field square inside the cavity, which is essentially the photon number inside the cavity. Okay. And this cavity is driven from the outside with some laser. Now, the interesting point is that this photon number or the electric field inside the cavity, this is the mean field, mean electric field is alpha. This mean electric field inside the cavity is not a given static number, but really that actually also evolves with time. And it evolves with time based because my atomic degree of freedom, so my Bose-Einstein condensate wave function, that can actually be a function of time. I can have some dynamics here. If I move my cloud, that changes my alpha and I can get some dynamics. So this means that the light induced potential that is inside a cavity is somewhat more exotic than the regular optical lattice, because it allows for the atoms not just to move in some fixed potential, but the atoms can back act on the potential itself. And this is beautiful because this does two things. One is it leads to rich many body phenomenon and condensed matter phenomenon, because this is somewhat closer to what happens with electrons in a solid. For example, the most famous example of this is superconductivity, which you cannot have unless there can be electron phonon interactions. Phonons are the lattice, so there is the electrons actually backact on the phonons of your metallic lattice to get a superconducting state. So this possibility of the degrees of freedom, like our atoms, to influence the potential in which they are moving will lead to interesting physics that way. The second beautiful thing that can happen is, because the light inside the cavity eventually leaves the cavity, I can actually use that as a beautiful non-destructive probe of the atomic dynamics. And this way I can actually see quantum phase transitions in real time, which has been done, or I can also use this as a sensor. For example, if I can use the atoms to sense a force, I can read out the force from the light of the cavity. Okay, so these two features, that you get truly interesting coupled dynamics between light and atoms, as well as you can use light as a probe to study the atoms. These two things make the study of Bose-Einstein condensates in a cavity a very interesting field, with many interesting open questions and many interesting follow-up questions, some of which among others, I'm looking at, like many people, I'm looking at that as part of my research. Okay, so let me quickly go to the conclusion slide and conclude, and we can have, if there are more questions, we can have discussion. So we've managed over the last 5 days to understand, or at least partly understand, what is a Bose-Einstein condensate, the Gross-Pitaevskii equation, Bose-Einstein condensates in optical lattices, and cavities as a quantum simulation, and sensor problem. This last part I did not really talk in detail about. Just, I hope I was at least able to convince you that this is a young and exciting field in some sense. It's only like about 20 years old, and the theory predictions can be tested within your academic lifetime. In fact, I have been also lucky enough to get that opportunity to propose something in my PhD, and by the time in my postdoc, something I proposed could really be tested in a lab, and I could work on that experiment as a theorist. So this is an opportunity that is, I would say, rarely available in physics, and that is one among the many reasons that you should consider ultra cold atoms seriously if you're not working on it already. Okay, that's it. Any questions?